Alright, hello class. Today, or in this video, we're going to be looking at section 2.3, which is over the algebraic limit theorems. So the motivation behind this particular section shouldn't be much of a surprise, really, because what we're trying to get at is, well, okay, so last time we proved something like this, that n over 2n plus 1 converges to 1/2. All right, and to do that, we had to show that basically we had to get like a capital N such that all n greater than this sort of goalpost would cause this distance between the two things to be less than epsilon, right? So we, cranked, I think it was a little different than this, but we sort of cranked through this, got 2n minus 2n plus 1 all over 2 times 2n plus 1. All right, and we want this less than epsilon. And so the two n's cancel, and we get the absolute value of, that would end up being -1 over 4n plus 2. All right, and then this will give us 1 over 4n plus 2. And, we would continue in this manner. And so, it might not have been that difficult to do. Okay. However, while it, isn't that bad in maybe a case like this, if we just eventually got to something like, n squared plus 5n plus 1 all over n cubed minus 13n squared plus 15n plus 11, if we wanted to show that that converges to 0, well, trying to do it with this epsilon and finding the n and all that is going to be a huge pain in the butt here, okay? So that's what leads us to wanting to simplify this process, and the algebraic limit theorems are basically going to let us, if we have something like this, right, and I'm taking, say, the limit of all this, the algebraic limit theorems are what's going to let us do this thing here, where we take the limit of the top and the limit of the bottom, okay, and then also these algebraic limit theorems are going to let us distribute the limit across and through the constants and all that. So it's another application of the algebraic limit theorem that is going to let us say that this is now the limit of n squared plus the limit of 5, limit of 5 times the limit of n plus the limit of 1 all over the limit of n cubed minus 13 limit n squared plus 15 limit n plus limit 11. Now, this is not exactly how we would do this problem. First, we would actually divide through by the highest power of n before we got to here, but I just wanted to show that this is what the algebraic limit theorem allows us to do. It allows us to move things across fractions and multiplications and ignore constants and all those limit rules that you take for granted from calculus, specifically calculus 1, that's what this section is going to give us. All right, but there's a couple of things we need to actually take care of ahead of time. Okay, so first what we need to do before we can really get into this is we need to define what it means for a sequence to be bounded. And I think that's probably kind of self-explanatory. Basically, a sequence is bounded if there exists a number m such that the absolute value of every term of the sequence is less than or equal to this m for all n in the naturals, or really for all n that the sequence is defined for. Okay, now this is similar to saying that equivalently we could say that xn is in the closed interval negative m to m for all little n in the naturals. Okay, so if a sequence is bounded, that means we can find a closed interval that every term of the sequence lives in. Right, so if our sequence is bounded, that means no matter what's happening with it, right, and remember it'll have an infinite number of values. If it's bounded, then I can basically find maybe it's an m here. I don't know if this is negative or not, but I can find an m such that if I take the absolute value of every term, all the terms are going to be basically less than that and stuck in this particular interval. Okay, now from here we get an interesting theorem. In the book it's listed as theorem 2.3.2, okay, which says that every convergent sequence is bounded. All right, so that should hopefully be somewhat not maybe easy to understand, but hopefully that does make some sense, because if we think about if a sequence, say we're looking at a k, okay, if this sequence converges to A, then at some point, right, every term of the sequence has to get really close to A. So if you remember, for every epsilon that we find, we have to have an infinite number of terms between the sequence and its limit. Okay, so at for this particular epsilon, so for this epsilon, all right, there exists a capital N such that A sub n is in the, let me write it like this, the epsilon neighborhood around A, okay, for all little n greater than or equal to this capital N. So that means outside of this set here, there's only a finite number of values from the sequence. So maybe A1 is here, and maybe A2 is here, and A3 is here, and on, and we go along, and then here is maybe a capital N minus 1, and then our first a(n) is in there, and everything after that is in there. Okay, so what that actually means is, since there's only a finite number of things outside of this little interval, and then every other term of this sequence is inside of this little interval, it's hopefully not too hard to see that this has to be a bounded sequence, right? If it's converging, everything is within this little epsilon neighborhood, and only a finite number of things are outside of this epsilon neighborhood. So we could pick our m right here, right? Provided this is positive. If it's not positive, we'll just go out until it is, right? Just pick something positive that's greater. Or you could always just pick the maximum value on the outside, right? Now, if all the ones on the outside are lower, then there's, you would have to do something else. But hopefully this little bad drawing I've done shows that if a sequence converges, then we have to be able to find an m that bounds all of them. Okay, so let's prove this, and it's going to be similar to this right here, this little picture. Okay, so I'm going to clean this up a bit and then start working on the proof. All right, so I'll leave most of the picture here. I just got rid of that blue outline there. Notice that this little drawing I've done is going to be true for really any epsilon I choose. I could choose a really small epsilon, and I would still have only a finite number of things sitting outside of it. So given that, we could actually approach this proof with maybe a nicer epsilon, maybe let it equal 1 or 1/2 or something like that. Okay, so that's what we're going to do. All right, so we need to start with a convergent sequence. So let's suppose the sequence x sub n converges to, let's say, y. Okay, so this means for any epsilon, I can choose a capital N or find a capital N such that the distance will be between epsilon. So, given epsilon equals 1, okay, we can find a capital N in the naturals such that given n, little n, greater than or equal to big N, we have that the absolute value of xn minus y is strictly less than our epsilon, which we've chosen to be 1. Okay, or if we're talking about the set definition, okay, what this means is if here's y, all right, and here is y plus 1, and here's y minus 1, right? That was my epsilon. All of the xn's past capital N live in here. So this is all of my xn's for n greater than or equal to this capital N. And then we have some other x's sitting outside. So, x1 might be here and what have you. All right, so just by the definition of either this open set or manipulating this, we have that the terms of xn are within y minus 1 and y plus 1, right? Trapped between y minus 1 and y plus 1. Now, the only thing I have to really be careful about is I don't know if y plus 1 is positive or negative. Okay, so, and let me also say, this is only true for the little n's greater than or equal to the big N. Okay, so I don't know if this is positive. Just in case, though, here's what I'm going to say. If so, all my xn's are going to be less than y plus 1, which will be less than or equal to the absolute value of y plus 1. So that's how we can deal with that. If y plus 1 ends up being negative, well, we can just do this because this will always be true. So this implies that the absolute value of xn is less than or equal to y plus 1 for n greater than or equal to capital N. Now you might think we've got it. You might think, oh wait, okay, our sequence is bounded, right? We have xn's, the absolute value of xn less than or equal to this thing here. But remember, if I scroll back up, it takes a while. Notice a sequence is only bounded if there exists an capital M such that it's greater than the absolute value of every term for every n. So all the n's, not just the ones greater than this capital N. So all we need to do, though, to fix this, so we're almost there. All right, there's one little thing we need to do, and that's basically we have all of these other x values out here. So there might be some out here that are outside of this open interval, this epsilon neighborhood, that might actually be greater. So we might have like x7 might be out here. So x7 might actually be the highest term of the sequence. So we just need to figure out a way to deal with that, because if y is positive, then this would be the absolute value of y plus 1, and then this value would actually be higher. So we couldn't use this particular value as our candidate for the maximum, or for the bound, for the upper bound. So we just need to take care of this. So basically, to shore this up, let capital M be the maximum of the absolute value of x1, the absolute value of x2, the absolute value of x3, all the way up to the absolute value of x capital N minus 1. And then, let me give myself just a little more room here. And this absolute value y plus 1. Okay, so if I let M be the maximum of basically all the finite terms out here, and we're taking the absolute value just to make absolutely sure it's all positive, and this bound candidate we got from the epsilon neighborhood. Okay, so we're just going to take the max of all of them, and we can do that because this is just a finite number of the x's, and then every other x, its absolute value is less than this. So we can just take the max of this and be confident that this m is greater than every xn. Okay, so we're going to let this capital M be the max, then okay, the absolute value of xn is going to be less than or equal to capital M for all little n in the naturals. And that's that. All right, so there's the proof of that. What I do want to mention, though, is this does not work in the other direction. All right, so this does not work in the other direction. In other words, just because a sequence is bounded does not mean it converges. All right, so just because a sequence is bounded does not mean it converges. For example, take the sequence xn that does, let's just say 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, on and on and on. This sequence is definitely bounded. Okay, by 1, right? Since the absolute value of xn is going to be less than or equal to 1 for all n. Okay, but xn does not converge. Okay, so keep this in mind, that convergence implies bounded. But bounded does not imply convergence. Okay, that's a common mistake I see. So just keep that in mind, that if the sequence converges, then it's bounded. However, just being bounded is not enough. We will get to another condition, that if it's bounded and something else, another condition, then we can get convergence. But yeah, just being bounded is not enough. Okay, so now we have everything we need to prove the algebraic limit theorem, which I abbreviate to the ALT, and this basically gives us everything that we need to make proving limits a lot more straightforward. Okay, so to start, let the limit of AN go to A and the limit of BN go to B. Then, part A, the limit of C times AN is equal to C times A for all C and R. So this is a constant multiplication. Right? This is our constant multiplication rule, which basically says we can move the limit inside and just say C times the limit of AN, which is A. Okay? Here's the sum rule, that the limit of AN plus BN is equal to A plus B. So this is the sum rule, essentially. Okay, here the limit of AN times BN is A times B. Right? That's the multiplication rule. And the limit of AN over BN equals A over B, provided our B is not equal to 0. There's our division rule. Okay. All right. All right, so let's go about proving these. We're going to start with A. Okay, so we're going to start by, of course, we always let epsilon be greater than 0. Okay, and we want to show, we're looking at the limit c times an. All right, so we want to show that we can find an n right, such that the absolute value of c times an minus c times a is less than epsilon, basically for all little n greater than or equal to this big N. All right, and to do this, well, I can actually factor this c out. So let me just put an i.e. We want to show this, that the absolute value of c times an minus a is less than epsilon. But this absolute value of an minus a, since an converges to a, we can make this absolute value of an minus a as small as we want. Right? Since it converges, since an converges to a, we can find an n that will make this happen. So, let n be such that the absolute value of an minus a is strictly less than epsilon over the absolute value of c. Now we're making a big assumption here, provided c does not equal to 0. All right, we'll talk about the c equals 0 case in just a second. But we can do this step here, one, provided c is not equal to 0, since an converges to a, right? Because it converges to a, we can get this distance as small as we want. We can always find an n that will get it as small as we want for all little n greater than or equal to this big N. Okay? And this is going to give it to us. This is essentially it. So, for all n greater than or equal to this big N, the absolute value of CAN minus CA is equal to the absolute value of C times the absolute value of AN minus A, which is less than, right, the AN minus A piece is less than, so I'll leave the C, times epsilon over C, which is equal to epsilon. So we actually got that the distance we're looking for is less than epsilon given any arbitrary epsilon. Okay? Therefore, CAN converges to CA. Okay, and that will end the proof. And I want to talk about this thing we just did here. This is how a lot of these proofs go. Remember, if AN converges to A, right, we can find an N where all the terms of AN minus the limit of AN we can get this absolute value less than anything we want. So here's the magic. We want this CAN minus CA to be less than epsilon. To do that, we get this sequence that we already know converges. So we know this converges. All right. And because of that, we can always find an n that will get it less than anything we want. So we want this guy less than epsilon, so we can put this thing less than epsilon over the absolute value of c. Okay. Now, of course, I forgot, if c is equal to 0, then we have a much easier time, because then c times an is going to be 0 for all n. So 0 times an converges to 0. All right, that's no problem, and that truly finishes off the proof. Okay, so hopefully as we do a couple more of these, it will start to maybe make some more sense. So let's do that. Let's prove part B now. Okay. Now part B, for the proof, we're going to let epsilon be greater than 0, of course. And we want to find, so I'll just say we wish to find an n in the naturals such that the absolute value of an plus bn minus a plus b absolute value is less than epsilon for all n greater than or equal to this capital N. Okay, well, it turns out that we're going to use the triangle inequality here. So from the triangle inequality, okay, I'm going to basically reorder this a little bit, right? This an minus a plus bn minus b is going to be less than or equal to the absolute value of an minus a plus bn minus b. All right, and we want this less than epsilon. Okay? And we know that these two converge. So we can get them as small as we want. We can get these two things together, even added together, less than epsilon. All right, and here's how we do that. We're going to actually get them both less than epsilon over 2. It doesn't have to be epsilon over 2, just for the record. It could be epsilon over 10, epsilon over 100. Anything that's going to get these guys less than epsilon. We're just choosing epsilon over 2 because that's traditionally what's done. But we could do epsilon over 200 if we wanted to. All we need is these two things to be less than epsilon when we add them together, which we can do because we know they converge, and because of that we can get their distances here as small as we want. So since AN converges to A and BN converges to B, we can get the distances AN minus A absolute value and BN minus B absolute value as small as we want. Right? Say smaller than epsilon over 2, for example. It just happens to be the perfect thing that will work for us. So, to be more formal, all right, more formally, and this is where I think people start to have issues with this stuff, because a lot of books kind of jump just to this next sentence I'm about to write, and they don't really write any of this stuff here. But more formally, choose in subscript 1, and I'll go ahead and be formal and say it's in the naturals, such that the absolute value of AN minus A is strictly less than epsilon over 2 for little n greater than or equal to n sub 1. And choose n2 in the naturals such that the absolute value of Bn minus B is strictly less than epsilon over 2 for little n greater than or equal to n sub 2. Now, I have to do it this way because this may seem kind of odd, right? But the goalpost, right? The point where AN gets within epsilon over 2 may take longer than it takes B, or it may happen faster. So to show it on a graph, if this is our epsilon over 2 and here's A, and then here's B somewhere else, it's the same epsilon over 2, but the first guy to jump in here may be A100, whereas the first B to jump in here might just be B10. Okay, so we do have to account for the fact that these two sequences may be behaving differently. In fact, not maybe, they most likely will be. Okay, so now we just want to take the largest of these n's. Okay, because if we take the largest one, say if it takes 100 for A to get into here and 10 for B to get into here, well, if we just chose n to be 100, well, we know B100 and everything past it is in here too. All right, so we just take the larger of the two. So letting capital N be the maximum of N1 and N2. All right, so letting our normal N be the max of these two, we will have, all right, that the absolute value of AN plus BN minus A plus B. So now I'm being super formal here. I'm starting with the sequence I want, or let me rephrase that. I'm starting with the distance I want, okay, less than epsilon. And then I'm going to start manipulating it, but now that I have all this, all right, this I'll rewrite. That's an minus a plus bn minus b, right? And that's going to be less than or equal to an minus a plus the absolute value of bn minus b. This is the triangle inequality. And these, well, this one will be strictly less than epsilon over 2, and this one will also be strictly less than epsilon 2 for all little n greater than or equal to our big N. Okay, which is epsilon. Okay, so there exists an N such that the absolute value of an plus bn minus a plus b, absolute value is less than epsilon for all little n greater than or equal to big N. Therefore, an plus bn converges to a plus b. Okay. So hopefully going through these two, it's starting to help a little bit. We don't have time really in this particular video to do the part C. We will look at part C and part D. Okay, so we'll do that in the next lecture video. Okay. And besides, I definitely think this is enough to throw at your brain in one video, in one day. Okay, so I will tell you, though, that it's normal if this kind of feels weird the way we're doing this, but just keep in mind how it always works is once you get what you're looking for. So here's the sequence we're looking for. So we want convergence here, right? So once we have that sequence that we want convergence with, if we can break it down to sequences that we know converge, then we can get those distances as small as we want, less than anything we want, whether it's epsilon over 2, epsilon over 100, less than anything that's going to help get you where you want to go. That is what you do. And if you know that a sequence converges, you can always do this. That is the formal definition of it, that we can get this distance as small as we would ever want, including epsilon over 2, epsilon over 100, epsilon over 1,000,000. All right, so that should be enough for this one. I'll catch you all in the next one. Cheers.